We have talked a lot about AI on this channel, but in today's tech landscape, there are a lot of interesting technologies that are powering the developments in the field of AI. And today, I'm going to talk about computer vision. What is it? And how is it related to AI? Make sure to watch till the end, because you know good things take time. So, as the name suggests, computer vision is an area that helps computers look and learn about the contents of images. I know that sounds bland and something very easy to achieve, but it is not how you perceive it. The reason is that computers are unlike humans who can just look at an image and grasp everything about its contents. So, it has been a challenge to achieve human-level perception on transistor-based devices. The complete procedure encompasses capturing images, filtering, scrutinizing, recognizing, and extracting data. This comprehensive process enables computers to understand visual content and respond appropriately. Think of computer vision as a puzzle made up of different pieces from various fields, like artificial intelligence, AI, and machine learning (ML). It's a bit like putting together a jigsaw puzzle, where some techniques are borrowed from different areas of engineering and computer science. So, how do the clever algorithms behind computer vision work? These algorithms rely on recognizing patterns, much like how we humans recognize faces or objects. One popular technique is using convolutional neural networks, or CNNs, which are trained on massive sets of images. During training, computers process these images, label the objects within them, and identify patterns. For instance, if you feed the computer loads of cat images, it'll learn to recognize the common features that make a cat a cat. This results in the computer being able to accurately decide if a new image contains a cat or not. Computer vision is everywhere in today's internet-driven world. From social media to online storage, images dominate the online landscape. With the power of modern computing, we can analyze this flood of visual data with ease. Computer vision has seen an incredible growth spurt in recent years. Thanks to improved hardware and advanced algorithms, accuracy in recognizing objects has skyrocketed from 50% to an impressive 99%. Surpassing human accuracy in many cases. No wonder why these techniques are super helpful in forensics. The applications of computer vision are vast and diverse, and it is by no means something new. It all started in the 1950s with some early experiments, but it wasn't until the 1970s that it became commercially viable, initially to differentiate typed and handwritten text. Nowadays, computer vision saves time and money in various fields, such as manufacturing, transportation, healthcare, and sports. It's used for everything from identifying defects and detecting intruders to monitoring crops and analyzing customer behavior. Some of the most common applications include identifying objects in images, detecting their presence, pinpointing key points in objects, segmenting object pixels, and recognizing objects while also determining their location. Projects in computer vision convert digital visual data into precise descriptions to amass multi-dimensional information. After that, this information is transformed into a format that computers can understand, facilitating decision-making. The primary aim of this subdivision of artificial intelligence is to educate machines in extracting information from individual pixels. In the past, machine learning algorithms found utility in computer vision tasks. But today, deep learning techniques have emerged as a superior solution within this field. This is because machine learning approaches demand massive data volumes and vigilant human oversight during the early stages to guarantee high accuracy, whereas deep learning takes a different route. Deep learning harnesses neural networks and leverages illustrative instances to tackle problems. It autonomously learns by utilizing labeled data to identify prevalent patterns present in these instances. Deep vision is just a step forward in machine learning, so my jigsaw puzzle still holds. You must be wondering that, okay, computer vision is used for image processing tasks, but why is it so important that it is among highly demanded professions nowadays? Look, the sheer magnitude of visual content shared online is staggering. Over 1.8 billion images are uploaded daily, and that's only counting the uploaded ones. If you factor in the images stored on mobile phones, the numbers would have been even more astounding. On top of that, we watch over 4,146,600 YouTube videos and send out 103,447,520 spam emails every single day. And that's just a slice of the pie. Communication, media, entertainment, and the expansive realm of the Internet of Things contribute significantly to these figures. Amid this deluge of visual content, the need for analysis and comprehension becomes unignorable. This is where computer vision steps in, training machines to effectively see and interpret these images and videos. The widespread availability of the Internet, made possible by seamless connectivity, exposes people of all ages to its reaches. Unfortunately, this accessibility also renders individuals, especially children, vulnerable to online abuse and negativity. Beyond its ability to automate various tasks, computer vision serves as a crucial tool for supervising and monitoring online visual content. Among the pivotal tasks in managing online content is indexing, with internet content predominantly falling into three categories: text, visuals, and audio. Categorization becomes more manageable. Computer vision employs algorithms to comprehend and categorize images. Prominent search engines like Google and YouTube rely on computer vision to sift through images and video, ensuring their appropriateness for publication. This not only provides users with pertinent content, but also safeguards against online abuses and harmful content. So, as I promised to talk about an interesting development in this field, I think now is the right time. Long story short, a machine named AI demonstrates an exceptional ability to process and analyze colors with an unparalleled precision compared to its predecessors. I decided to make a video on this after reading an extensively detailed research paper published in Materials Today. This paper elaborates on AI's capabilities. In an age characterized by escalating automation, colors and shapes stand as primary features frequently employed in object recognition tasks. As automation continues its ascent, the proficiency of machine learning in perceiving color becomes progressively indispensable. AI's innovation encompasses a dual impact, as the researchers concurrently achieved the creation of two-dimensional materials imbued with unique quantum properties. These materials, woven into an optical window, grant entry to light and empower the device to meticulously process a wide spectrum of colors with great accuracy. Let me tell you one thing, before this machine, this feat was considered unsurmountable. So this is a big achievement that represents an evolution that defied prior limitations in computer vision research. The success of AI owes much to the collaborative synergy between Northeastern's Quantum Materials Lab and Augmented Cognition Lab. This union has yielded machine learning algorithms that exhibit exceptional precision in color detection and reproduction. The crux of this milestone rests in the optical and quantum attributes of a specific class of material known as transition metal dichalcogenides. These materials have long been acknowledged for their untapped potential across domains such as electronics, optoelectronics, energy storage, and sensing applications. The remarkable breakthrough hails from the behavior of light as it traverses quantum matter. The material, transition metal dichalcogenide, when grown on a designated surface, imparts the ability to generate an electrical signal when sunlight permeates it. This signal serves as valuable data that feeds into machine learning algorithms. That story does not end here. A key player is the detection and interpretation of colors. Traditional methods involve breaking down colors into their red, green, and blue constituents. However, this method has inherent limitations. The innovative computer vision AI technology circumvents these limitations by replacing traditional RGB filters with transmissive windows crafted from the specialized two-dimensional material. This new approach leverages the full spectrum of spectral information rather than segregating colors into the primary RGB components. Consequently, a more unique and accurate representation of the original colors is achieved. When light interacts with the device's windows, it embarks on an analytical journey as data. Machine learning models dissect this data, identifying intricate patterns that correspond to each color. This process refines the device's color perception, continuously improving through the incorporation of corrected predictions into its training database. An indirect way to empower computer vision is to make deep learning more enabled. And that is happening too, because the realm of deep learning AI has received a substantial boost from the groundbreaking hardware development. This hardware emulates the structure of the human brain and falls within the category of neuromorphic computing chips. These chips display immense potential across artificial intelligence and machine learning applications, including computer vision and deep learning. However, conventional electronic circuits limit the speed and complexity of these chips as they grow in size. Researchers at the National Institute of Standards and Technology have addressed this limitation by employing a novel approach. This approach involves the integration of tiny light sources within each neuron, emitting optical signals across thousands of connections. By utilizing superconducting systems to detect photons, the smallest optical signals, these neural networks can outperform traditional chips. NIST circuit, functioning like a synapse in a biological system, uses single photons to send and receive signals. The Josephson junction, a superconducting element within the circuit, plays a crucial role by engineering voltage pulses or fluxons when activated by a photon. Subscribe to Innovella for more blues from the world of AI. Just like this one, I've made another explainer on neural networks. If you are an AI freak, that video is a must-watch for you. It's on your screen, so click now, and I'll catch you there in a second.